I start? Huh? Okay, fine.
Okay, so let's start with the lecture. So Nitiman will continue talking about the Torus code
Okay. Okay, so since this is a new lecture, let's have some new notation, which is more convenient. Okay, so we have a square lattice with spin half degrees of freedom sitting on the midpoints of the bonds. Okay. So I can label a side by, let's say, I. So one new notation which is saves us a little bit of writing is instead of sigma I x, let me just call it xi. Okay. And sigma I y, sigma I z, let me call it zi. Okay. So the idea is that xi squared is equal to zi squared is equal to 1, xi zi is equal to minus zi xi, and at different sides of course they commute. So xi xj is equal to xj xi, etc. The Hamiltonian is minus, and then I will call this coefficient j instead of alpha. So then it is sum over sides, A sides, minus j sum over plackets, B plackets. So so if I call this 1, 2, 3, 4, this is a site S, then A at that site S will be x1, x2, x3, x4, and if I introduce two more sites, let us say 6, 5 and 6, then so this is AS, this is going to be BP, so BP will be Z1, Z6, Z5, Z2. Okay. So that is the Hamiltonian for the toric code. Okay. So as I said earlier that all these ASs are Hermitian, AS, BP are all Hermitian, and the square is 1. And they all commute. So A's commute with A's, B's commute with B's, and A's and B's also commute. So that means that because they all commute, the ground state energy is just equal to minus j sum over number of sites plus sum over number of plackets. Okay, so the energy is very simple, but what is the state, ground state? And that is not so simple. Now, so let us try to figure out what is the ground state. So, because BP is the sum over is the product of 4 z's, if I take a state where all the z's are plus 1, right. So, if I take a state which is all zi equal to plus 1, so all of them are up. So, this is the ground state of the second part of the Hamiltonian clearly, right. Okay, so, this state psi, which is all spins pointing up, is a ground state of the second part of the Hamiltonian, minus j sum over p BP. However, it is not a ground state of AS. Okay. In fact, you can see that if you act with AS on psi, then this is a state where all Z I is equal to plus 1 except for the 4 sites on which AS acts, and AS is a product of sigma x's. So, what it does on those 4 sites is that it flips up to down. Okay. So, this is a state where the spins are up everywhere except on the 4 sites where they are down. Is that fine? Okay. So, you can see that it is not very easy to write down a state for which is a ground state of all the AS's as well. So, however, you can, there is a trick you can use, which is that because the AS as a Hermitian operator square is 1, so the eigenvalues of AS are plus or minus 1. You can write down an operator which is a projection onto AS equal to plus 1. Right. So, to get the ground state of that Hamiltonian, you want a state which is an eigenstate of all the AS's and BP's with eigenvalue plus 1. So, you want to project onto states which has AS equal to plus 1. So, the projection operator, projection to state with AS equal to plus 1 is half 1 plus AS. This is true for any S, right. So, this is the projection operator, right. You can easily check that, because if you take the square of this projection operator, this is just equal to 1 plus AS, okay, because of this property. So, that is the property of projection operator, square is the same. So, sorry. So, first I started with something which is a ground state only of the BP's, and that is a state with all spins up. But I am now going to do something to that ground state, act on it with something which makes it a ground state of the AS's also. Okay. So, what you do is that you take this ground state, all spins up, and then you act on it with the projection operators for all the AS's. Okay. So, the true ground state of this problem, which has all these terms, so the actual ground state is product over all the S's, 1 plus AS over 2, acting on the state where all Zi equal to plus 1. Okay, so that is the ground state. You can see that this is actually a very complicated state, because in this product, if there are n sites, then there will be 2 to the power n terms here. So, you will have a superposition of 2 to the power n states, okay, and they are very complicated. So, when a single AS acts on the state, you flip the spins on those 4. Then if you have a product of 2 S's acting on it, then you flip 4 spins here, 4 spins there. If you have 2 S's next to each other, one here and one here, you flip these 4 spins and these 4 spins, which means this spin actually remains the same because it is flipped twice. So, you flip these 3 spins and these 3 spins, and so on. So, this is a state which is a superposition of an exponentially large number of states with various combinations of up and down spins, except that you always have an even number of up spins and even number of down spins, if the total number of sites is even. Okay, so it is a very complicated entangled state actually, and we are not really going to work with this, but this is just to show you that you can formally write down the ground state of this Hamiltonian, okay, and that is the energy. Okay. So, next thing I want to show is this idea of topological order. So, if you now put periodic boundary conditions in both directions, what I will show is that there are 4 states which all have the same energy. Okay. So, that is a statement. On a torus you have 4 degenerate ground states. Okay, so this picture I am not going to erase. There are two kinds of terms in the Hamiltonian. One is the product of x, 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 and the other one is the product of z, 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 z. Okay. Hamiltonian is minus j sum over s a s plus sum over p b. Okay. So, first of all, it turns out that there are 4 operators which are kind of global operators. They involve a product of strings running over the entire system. 2 of them will be running over in the horizontal direction over the entire system, 2 of them will be running in the vertical direction. There are 4 such operators which all commute with the Hamiltonian. Okay. So, what are these 4 operators? So, one operator is if I take a product of z's, right. So, it is a product of z's, let us see, yeah, it is a product of z's running in this direction, right. I mean z is sigma z. Okay, so, this product, so product of z's in this direction, you can see that this commutes with the Hamiltonian. The reason is that it of course commutes with the BP because those are only made out of z's. It also commutes with the AS because every AS has an x and an x here, and that string has 2 z's. So, this z anti-commutes with this x, this z anti-commutes with this x. So, that product commutes with this product of 2 x's, and that will be true for every site. So, every site has 2 x's in the vertical direction. So, it will commute with that. So, that is one operator which commutes with the Hamiltonian. So, let us give this a name. So, I am running out of symbols. Let me call it C1. Another conserved quantity is product over z's running in the horizontal direction. So, I take a z here, take a z here, take a z here, take the product of z's that way. This also commutes with the Hamiltonian because for every AS term there is a z here and a z here. Okay, so, product of 2 of those z's will commute with the product of 2 of these x's. Okay, and that is true for every AS that you can think of, right. So, this also commutes with the Hamiltonian. Let me call it C2. Okay. So, there are 2 more that we need. Okay. So, the other 2 will involve products of x's. So, suppose I take a product of x's like this. That commutes with the Hamiltonian because of course, it commutes with these AS terms, but when it comes to BP, for every BP that has a product of an x here and an x here. So, there are 2 x's, so that commutes with 2 of the z's. So, that commutes with the BP. So, I will call that D1. So, we have to find one more. Yeah, so the other one runs, how does it go? So, I take Zex So, product over x is like that, and that is d2. That comes with the Hamiltonian, because for every placket part there is an x here and an x here. So, that commutes with this. So, we have 4 operators and they all commute with the Hamiltonian. Okay. Yes. So, I am just coming to that. So, C1, C2, D1, D2 all commute with H. You can also see that they are all Hermitian and all of them square to give you 1. Okay. So, the eigenvalues are plus or minus 1. Okay. So, now let us look at the commutation or anti-commutation relations between these C's and D's. Yeah, you have to assume that this thing goes and closes. So, basically it is going to be a loop. This is a loop of z's going around like that. This is a loop of z's going around like this. Yeah, so you have to use periodic boundary conditions in both directions. Otherwise, you will have a problem with the last placket or the last site. Yeah. Yes. So, we are just going to do this on a torus. Okay. Okay. So, let us look at commutators. So, C1 of course commutes with C2 because they are only made out of z's. D1 commutes with D2. How about C1 with D1? So, C1 and D1 commute because the C1 has z's on the vertical bonds, but D1 has x's on the horizontal bonds. So, they are different sites. So, C1 and D1 commute. But C1 and D2 does not commute because so at some point there will be C1 has a z on a vertical bond and this will have an x also on a vertical bond. Okay. So, these will have to cross on some vertical bond somewhere in the system. So, when they cross, because this z and x anti-commute at the same site, right, the sigma z and sigma x. So, C1 anti-commutator with D2 is 0. So, similarly you can show that C2 commutes with D2, but C2 anti-commutes with D1. Okay. So, that is the structure of commutators and anti-commutators for these 4 operators. Okay. So, now here is the claim. The claim is that suppose C1 and C2 of course commute. So, suppose you label your states using eigenvalues of C1 and C2. So, the eigenvalue of C1 can be plus or minus 1, eigenvalue of C2 could be plus or minus 1. So, there are 4 possibilities, eigenvalues of C1, C2 plus plus minus plus minus minus plus minus minus. So, those are 4 states. So, the claim is that those 4 states are degenerate with each other. Okay, so I am going to erase these pictures. Yes. Yes, so you have a lot of choice. You can take any string you like, but all these properties are independent of where you place this string. The only thing we needed is that this string, wherever you put it, will cross this string somewhere, wherever you put this. Okay, so these relations are independent of the location of the string. So, we are going to look at states which have C1, C2 equal to plus 1, plus 1, plus 1, minus 1, minus 1, plus 1 and minus 1, minus 1. And so, the next claim is that within these sectors, now of course, there are lots of states in each of these sectors, but the ground state of each of these sectors, the energy of all the ground states in these sectors are the same. So, how do you show that? So, you can't show that using only C1, C2, but to show that you have to use the presence of D1 and D2. Okay. So, let us call this state 1, let us call this state 2. Do I need to? No, we already have a notation, this is fine. So if I take D1 acting on +1 +1. So notice that D1 anti-commutes with C2. So that means that D1 acting on this gives you a state where this set, the second eigenvalue gets flipped, right. So this is the state which is +1 -1, right. Okay, so here we are using the fact that D1 C2 is equal to minus C2 D1. Okay, but the fact that D1 commutes with the Hamiltonian means that these two states have the same energy, right. So D1 with H is 0, so that implies that 1 +1 +1 and D1 acting on +1 +1, which is the same as +1 -1, have the same energy. Okay, so that proves the degeneracy of these two states. Similarly, you can use D2 to act on this state to produce a state which is -1 +1. So D2 acting on +1 +1 gives you a state which is -1 +1, and because D2 comes with the Hamiltonian, these two states must be degenerate in energy. And then you act on this with D1 and you get -1 -1, and that has the same energy. Okay, so this is a proof that these four states. So in particular, you can take this to be the ground state that I wrote earlier. I think it is actually in that sector. 1 plus A is by 2, all Zi equal to +1. You can take this to be the state and then act on that state with D1, D2 and D1, D2, and you get the other three states, and they all have the same energy. Okay, so this is a very clean proof that on a torus there are four states which are degenerate with each other. Okay. No, so the other, so this is the state which is G. This state will be D1 acting on that G. It's in a, so it's in a different sector. The eigenvalues of C1, C2 are different. Okay. All right. Now let me say briefly what happens if you have a finite system, because Anders asked this yesterday. So it turns out that if you have a finite length torus, then this degeneracy is broken slightly. Okay, and you can ask. No, it's still a torus, but finite length torus. Suppose. Okay. Now, as it stands, it's still going to be degenerate. If you take a finite length, a torus of finite length in both directions. But imagine that you perturb it a little bit, you add some extra terms to the Hamiltonian. So the question is whether it still remains degenerate or not, right? Okay. So let me be precise about what I'm saying here. So finite system with a perturbation. Okay, so now unfortunately, since I've erased things, somebody has to remind me what C1 was. It was a string of x's or what? Z's? Huh? Okay, so C1 is z's in the vertical direction. So it was a product like that, right? Okay. So imagine that we add a perturbation to the system. So this was, let's say, H naught. Now we take a perturbation V, which is a magnetic field H times sum over Zi. Okay. So this now breaks a lot of symmetries. All right, it no longer commutes with, it commutes with the BPs, but it doesn't commute with the ASs. So it doesn't commute with the Hamiltonian. So when you add a perturbation like this, because it doesn't commute with H naught, you would think that these 4 sectors will get mixed with each other. Okay. So you will not get a degeneracy of the ground state. But what you can show is that if you take a very large long torus, then you do get the degeneracy of the ground state. Okay. So this topological order, which is the fact that there are 4 degenerate states on a torus, that survives perturbations, provided the torus is infinitely long in both directions. So how do we see that? So I think I used the wrong perturbation. What was D1? Huh? All right, let's change the perturbation. Okay, we'll use both. I don't know which one I need, but I'll use both. So this is product over x's. So basically, what I'm trying to do now is see what is the Hamiltonian within this ground state sector. So the ground state has 4 degenerate states. So just within that space, we want to write down a 4 by 4 Hamiltonian and see whether what the eigenvalues of that Hamiltonian are. So there was this state +1, +1. Okay, so let me, now I really need a notation, I think. So I +1 -1, this was D1 acting on I, 1 gives you 2. So the question is there any mixing between these 2 states? Okay. So if let's just worry about these 2 states, let's ignore the other 2 states. So I'm trying to write down a Hamiltonian for these 2 states. So it will be a 2 by 2 Hamiltonian. So to begin with, without this perturbation, it's degenerate, right? So you have some number here. Let's make this 0. We can subtract out some number and make these 0. So without that perturbation, these are going to be degenerate. Now with this perturbation, so which is the perturbation that can mix these 2 states? So these 2 states differ by the action of D1, which is a product of all these xi's. So if you just have one of these terms, that's not enough to mix these 2 states, right? Because this xi, it can go and cancel one of the xi's, but the other xi's will still be there. And so this state will not be equal to, so you cannot get rid of this state by just acting with one of the xi's. Right? So what you need to do is act with this many times, so that you bring in enough powers of xi to cancel all these powers of xi. Right? So if the system has L sites in this direction, you will see that these 2 states mix only at the Lth order in perturbation theory. Right? In other words, if I call this x1, x2, x3, so you will have a term, you are starting with the state +1, +1, then you will have to add, multiply by hx1, then hx2, so on, till you get hxl, and then it will have a non-zero overlap with the state which is +1, -1. Okay. So is that clear? Right, because you have to put in enough x's which cancels out all the x's that are there in D. Okay. So this is Lth order perturbation theory. And of course, there will be a factor of j to the power L minus 1, the energy denominators in perturbation theory, which means that this is going to be a term which is of the order of j times h by j to the power L. So, that means this matrix element between these two states is of the order of h by j to the power L, h by j to the power L. So, now you can see that okay, so the true ground state of this is really I plus or minus 2, right, and the energies of these are plus or minus h by j L. So, there is a splitting, but the splitting goes to 0 exponentially if h by j is less than 1 and L goes to infinity. Okay. So, the energy splitting goes to 0 exponentially if h by j is much less than 1 and L goes to infinity. Okay, so, this just shows you that even if you perturb the system by terms which break the symmetries of the Hamiltonian, you do not break this degeneracy of the 4 states on the torus if your system is very, very large. Okay. So, you have this perfect degeneracy for infinite systems. So, that is showing that this topological order survives if you have some perturbations. Okay. That is true, yes. Yeah. That is true. Yeah. So, you are saying you should have an L factorial there. So, it is L by e to the power L. Okay. Yeah, because you are exponentiating h. Yeah. 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 Okay. All right. So, that is about the degeneracy on a torus and topological order. So, next thing I want to talk about is electric charges and magnetic charges, okay, and their mutual statistics. Yeah. Okay. So, the ground state has all A s equal to plus 1 and all B p is equal to plus 1. That is the ground state. Now, let us look at a state which is let us look at an excited state. So, it is clear that if I flip one of them, right, suppose I take only one of them and flip it from plus 1 to minus 1, then that is going to be an excited state, right. In fact, it will have an energy which is 2 j more than the ground state. Okay. So, this is a system which is gapped to all excitations. Okay. So, let us say we want a state, excited state with one of the As equal to minus 1, all the other ASs will keep them plus 1 and all the other BPs will keep them plus 1. So, how do you create such a state? So, the ground state, I call this G. So, imagine that So, let us take this ground state and act on it with an x sitting there, right. So, let us call this, give this a name, let me call it site number 1. So, if I take that ground state and act on it with x 1, then x 1 will that do the job? No, that won't do the job. Not x 1, z 1. Yes. Okay, so we act on it with z 1. So, you can see that z 1 anti-commutes with the product of these 4 x's, right, because z and x anti-commute at the same site. So, z 1 acting on g, it gives you a state which is, let me call it a 1. So, it gives you a state where a 1 flips from +1 to -1, right, because it anti-commutes with this x. But unfortunately, it also flips this a 1 to -1, right, I mean this a 2. So, there is an a 2 sitting there, where is it? There is an a 2 sitting there, which is a product of x's or these 4 sites, and a z acting on this, it anti-commutes with this x. So, it gives you a 1 -1, a 2 -1, and all other as and bp are equal to +1. Okay, so, it is actually a pair of excitations, it is not a single excitation, which is what we want. Okay, so, what do you do to get a single excitation? You act on this with a z now sitting there. So, if you act on it with the z sitting there, that will flip the sign of this a. So, that will become a +1, but the next a will flip to -1. So, this is a z 1, let us say this is z 2. So, if I act with z 1, z 2, they commute. So, it does not matter which order. So, now you will have a 1 is -1, a 3 will be -1. So, a 3 will be here, all the rest will be fine. So, you have separated out these 2 squares a little bit, but you still have 2 of them. So, you can see what you have to do, right. You have to multiply with a string of z's starting from this point going all the way to that end. Okay, and here it is convenient to again imagine the system is infinity, and this time we will not worry about boundary conditions. Okay, so, it is really infinity. Yeah. So, you have to have a string of zi's from I equal to j to infinity acting on g. This gives you a state with a j equal to -1 and all else, all other a and b are +1. Okay. Yeah, I know, but let us not mix different things. Yeah. So, so this gives you the string of semi-infinite string of z's from one point up to infinity, creates a state where you flip one of the a's to a -1. Okay. So, a state with one of the a's equals -1, let us call it a electric charge, and I will call it E. Yeah. Sorry? Yes. Yeah, I think that will be the effect. Yes. Yeah, absolutely right. So, this is equivalent to changing one of those projection operators from 1 plus a to 1 minus a.
Yes, but then it would be only a single square, a single a change sign, not a pair
no,
of
it will
them.
change only a single a. If you only change the projection operator from one of the a's to 1 minus a and keep all the rest the same, then it is exactly the state that you want. But I find it easier to write it in terms of some operator.
You showed that by a local operator you need to create them pairwise.
Yes. If you have a single operator, then you create them pairwise. But if you have a string of operators going up to infinity, then you can change it at only one side. Yeah, so it looks like the position operator, changing the position operator for a single A is equivalent to hitting it with a string of operators from that side to infinity. Yeah. Which others?
No, if you have only 1 minus A1, only one of the projection operators change.
Yeah.
I don't know whether it is going this way or this way.
So you have a lot of freedom about choosing your string. It just has to start from one point, but it can go to infinity in many different ways. But this is the simplest. It just goes from there to right. It can go to infinity in many different ways. Sorry? Yes.
I think if you apply one sigma z operator, then you flip two A's. Okay. So to flip one A, you would have to apply a whole string of operators, which is equivalent to the string operator.
What I'm confused with, sorry, I stop, so that people can get, is that there is a way to construct a wave function with a single A and a minus 1.
Yeah.
And here, we see that we cannot do it, we need the string. So there is some.
No, there is no local operator which would allow you to change one single A. So starting from the ground state, you cannot create a single excitation like that.
There's another. Yes, yes, I fully agree. So the creation when we change the sign in a projector is something different. And I mean, I wonder, for example, how your Hilbert space is quite large. I mean, you have 2 to the n
Right.
number of states, and
Right.
playing with the signs in the projector operators is just.
It actually
It's
changes
smaller.
an exponentially large number of. So even if you are changing only one position operator, in that large superposition, you are actually changing a huge number of terms.
Yes.
Yes. Right. Right. Yeah. I mean, you start with a ground state, but you hit it with a string of z's, and so it changes it in many different places. Okay. So a state of this, we'll call it a state with one electric charge. Now, this electric charge is a bit peculiar because you cannot create two of these at the same site, because if you create two of this, that's like not creating anything at all. Right? In other words, if I take the string of z's and then square it, it's just the identity. So this is an electric charge which is either 1 or 0. You cannot have charge 2. Charge 2 is the same as charge 0. It's completely, that's the totally arbitrary. You have to give it some name. So let's just call it a charge. Well, roughly speaking, it's called a charge because it's sitting at one side. The state where you excite one of these BPs, because it's on a placket, we'll call it a magnetic charge or magnetic monopole. So we just want to distinguish between the two kinds of excitations, excitations of A and excitations of B. So we give them two different names. So we're just calling them electric charge and magnetic charge. Okay. But the important thing is that it's an Ising charge, so you can either create it or not create it. You can't create two. That's the same as not creating it at all. Okay. The next thing is how do you create an excited state with one of the BPs equal to -1? Okay, let's draw this picture all over again. So let's say we want to flip this one, this B. So this is made out of Z's, and here are the X's. So what you should do is, sorry, let's just go back here. So the way you created this is by a string of Z's going from some point to infinity to the right, right. So, this was the creation operator for this is a string of I, yeah, it is here, j equal to infinity z I, going this way horizontally. Now, to create an excitation with, let us say, the B on this placket equal to -1, I can hit it with an X at this point, and that will flip the sign of this because X anti-commutes with Z, but unfortunately also flip the sign of this. Right. So, then what you have to do is that you hit it with the product of x's going all the way from here down to infinity. Right. So, the way you create this is that you act on the ground state with a product of x i's from, let us say, some j to minus infinity, and this creates an Ising magnetic charge so let us call that M for magnetic charge, and again you can only create one of them. If you create two of them at the same site, those two strings cancel each other. So, is that fine so far? Yeah. Now I am not, yes, true. So, if you have yeah, so I am now talking about very large system, but with open boundary conditions. If you really want to pin me down, let us say we have open boundary conditions. So, a chain like this will create an electric charge here, and it will create another electric charge which is at that end of the system, but it is infinitely far away. So, we are not worrying about that. Yeah, yeah. So, yeah, let's not confuse these two things, because I will confuse myself more than anyone else. So, that was about the topological order and torus. This is about electric and magnetic charges. We can combine everything, I am sure, but it is just too much for me to handle after lunch. Okay. So, the way you create, so let me repeat that. So, you create an E by a product of Z's running this way, and you create a M by a product of X running this way. And as I said, there is a lot of arbitrariness. You can take a product of Z's running this way to this end, and that will do as well. You can take a product of X's running this way. You can also take products running, in a zigzag way. As long as it goes off to infinity, it is fine. It is only the starting point which is important. That is where you want to create the electric charge or the magnetic charge. Okay. Okay, so now what we are going to do is we are going to figure out what kinds of statistics these particles. So, let us think of them now as particles. There are two kinds of particles, particles with electric charge 1 and particles with magnetic charge 1. You can even have bound state, right. You can have a particle with electric charge 1 and magnetic charge 1. So, you create that by multiplying the ground state by this string times this string. So, you can do that also. Now, suppose, so let us look at two electric charge particles and see what is the statistics of those two. So, if I want to create an electric charge here, so to create electric charge at site, let me call R1. So, the way we do that is that your product over R prime equals R to infinity Z R prime acting on the ground state R1. Then you can create an electric charge at site R2, that goes from r prime equal to r2 to infinity, z r2 prime, r prime acting on the ground state. By the way, you can see that these are strange objects because I am saying that this is the creation operator, but the square of the creation operator is 1 obviously, right, because square of every z is 1. So there is no difference between a creation operator and a destruction operator. Okay. So now, do you think these two commute? They commute, right, because each of them is a string of z's and all z's commute with each other. So that means two particles of both with electric charge are bosons because their creation operators commute with each other. Okay. So the E particles are bosons. In other words, if I create something at R1 and then create something at R2, that is the same as creating at R2 and then creating at R1. It does not matter in which order you create them. Okay, so the E particles are bosons. That is true. So hardcore bosons, yes. So is this okay? You can see that it is also true of the magnetic charge particles. So if you create two of them, because x's commute with each other, two magnetic charge particles also are bosons. So M particles are also bosons. Now, what about an electric charge particle and a magnetic charge particle? Now, those are not identical particles, right. So, you cannot really talk about exchanging E and an M, because if there is an E here and an M there and you exchange them, you get an E here and an M there, and that is not the same as what you started with. So, if you have non-identical particles, there is no concept of exchange. But as I said in the first talk, there is a concept of holding one fixed and taking the other in a closed loop around it. That you can still do, and you can ask what that does to the wave function. So this is called, so between E and M, there is something that we can calculate. This is called mutual statistics. There is the name given. And the way you calculate this is, let us say you hold M fixed and you take an E particle and you move it all around, either clockwise or anti-clockwise. This is a two-dimensional problem, right. So it makes sense to say clockwise or anti-clockwise. That is a fixed notion. In 3 dimensions, it does not make sense to say some is a closed curve is clockwise or anti-clockwise. So you take M, take E all around it. When you come back, then it is the same state as before. So you can ask whether the wave function of the state remains the same or if it has changed. So by the way, if you do this with two identical particles, and if you went all around, the wave function will always remain the same, whether E is a boson or a fermion. That is because for identical particles, you can show that keeping one fixed and taking the other in a closed loop around it is like doing two exchanges, right. It is like doing this and then another one. So when you have two bosons or two fermions, if you just exchange, you get +1, in one case -1. But if you do this closed loop, you get a +1 in both cases. Okay. Okay, so even here, when you do this E going around an E, you get +1, or M going around M. But for E going around M, it is not obvious what we are going to get. So let us do this calculation. Oh no. So how do you create an M particle? It's a string of x's going down.
It's okay, we intersect it once.
Yes, fine. It doesn't matter. I'd like to claim that I remember, but I'm just testing you. But it's not true. I don't really remember. So to create an M there, or really create an M here, you multiply it by a string of x's, right, going down. So a string of x's going down acting on the ground state is an M particle. So let's say somewhere I have an E particle, and this I create by a string of z's, right? Okay. So I have a string of z's which is, let's say, could go that way, but let's take it going this way, so that right away it doesn't go and intersect that. So I have a string of z's. So that creates a E particle, which is a string of z's acting on the ground state. And as long as these two are not intersecting, then you can do both. You can create both an E and an M, and it doesn't matter in which order you create them. Okay. Now we have to do this process where you hold M fixed and you move E. Okay. Now this is going to be a bit tricky. So how do you move E? So let's do it step by step. So when you have a Z here, this creates an E at I guess this site, right? Because it anti-commutes with the product of these 4 x's. So let's say I want to move it from here to here, right? So we want to go around. It doesn't matter this way or that way. If you want to move it from here to there, so you multiply it by, so you take the string and now I multiply by the product of these two z's, right? So I have this string that created an electric charge here. Now I multiply, so let me call it, I don't know, some random number, A, B. So if I multiply ZA, ZB acting on E, then, then this Z squared is 1, so it's gone from here, but now you have a Z here, and so you have produced an electric charge there. Yeah, so that was not a very good idea. I should put the Z here. Yeah, you're right. Otherwise, you'll create an electric charge here also. Yeah. So I move it here, right? Yeah. So I multiply it by a string of by product of this Z and that moves the electric charge from this side to this side. Yeah, so you are multiplying it by ZA times ZB acting on this. Oh, ZB is enough. Okay, good. You are right. Right. So this operator moves the electric charge from here to here. So then you can keep moving it like this, and you can form a closed loop like that. So basically, to move this electric field, so I guess I'm going in the other direction. Doesn't matter. I go in this direction. So if I take a product of z's over some loop like this, acting on E, that basically gives you this process where you move the electric charge in this way. Okay. But notice that, yes. So, when you move the z's around, you want to start here and come back here. So, you have a string of z's like that, somewhere it will intersect an x, right. So, this string of z's, which went around like that, with the string of x's that you require to create M, they anti-commute, right. So, this is equal to minus the product of x's with the string of z's, because this string of z's, it will actually cross only one of the x's or maybe an odd number. I mean, if you just take a curve like this, it will cross once. You could be perverse and take a curve like that, but then it will cross 3 times. So, it has to cross an odd number of times. So, these two will anti-commute. Is that okay? So, what that means is that if you take an electric charge around a magnetic charge, the wave function picks up a -1. Okay. So, the mutual statistics between electric charge and magnetic charge is a -1. So, it is kind of unexpected, right? It is not as simple as you thought. This is sometimes called a semyon statistics. Okay. So, I should explain this notation. So, this notation comes from this concept of anyons. So, you know, you have these hypothetical particles in 2 dimension, identical particles, so that when you exchange 2 of them, you pick up a phase e to the I theta. Okay. So, let me just talk about anyons for a couple of minutes. So, you take 2 particles and you just exchange them once. So, it is not a closed loop, exchange them once, you pick up e to the I theta in the phase. Here it matters whether it is clockwise exchange or anti-clockwise exchange. So, let us pick a convention. So, theta can be anything from 0 to 2 pi. In particular, if theta was 0, then these would be 2 bosons, right. If you exchange, you pick up a phase of 1. If theta is equal to pi, these would be fermions. And in general, it could be anything, and that is why it is called anyons. It is a terrible word, but you know, very bad joke. It is coined by Wilczek. So, theta is bosons, theta is equal to pi is fermions, theta equals pi by 2 is called semyons, right, because it is halfway, halfway between bosons and fermions. So, if you take 2 semyons and exchange them, the wave function picks up e to the I pi by 2 I. So, 2 semyons, if you exchange them in the clockwise sense, you pick up an I. If you exchange them in the anti-clockwise sense, you pick up a -I. Okay. So, now if you do a closed loop, if you take one of these particles and you take the other one all around it in a closed loop, you pick up e to the I 2 theta, right, because I said going around in a closed loop is like exchanging twice. So, if theta is pi by 2, you will pick up a phase of -1 if theta is pi by 2. Okay. So, that is why when you take one particle around another in a closed loop and you pick up -1, you call that semyon statistics. Okay. So, that is a little bit unexpected that this E and M, they actually have funny kind of mutual statistics. Yes. So, that is why you can only describe a statistics based on going around in a closed loop. You cannot describe what happens when you exchange them. Right. But the name semyon comes from that. Okay. So, I am almost at the end now. So, what happens now if I take a bound state of electric charge and a magnetic charge? I can do that, and as usual I have forgotten how you create it, but you created an E and an M somewhere by a string of Z's this way, X's this way and Z's that way. So you can so that means that this is a state in which, let us say, this A is a -1, and let us say this B is a -1, and everything else is +1. It's really not a physically bound state. I mean, there's no, I'm not talking about any energetics here. So I'm not saying that this has less energy than separate E and M. I'm just saying suppose they're close to each other. So think of this as a composite particle, which has both an electric charge and a magnetic charge. An object like this is sometimes called a dion, because it has both electric and magnetic charge. So it's sometimes called a dion. So what happens if you exchange two dions? So now dions should be identical particles, because this dion has an E and an M, that also has an E and an M. So for dions, you can ask what will happen if you exchange them. So here's an E and an M, and here's an E. Let me call it a E prime and an M prime. They're really identical, but I just want to distinguish between them. And let's say you do this. Okay, so you can actually figure it out in a rigorous way by drawing the strings of x and z's, but I am going to take a shortcut and just draw some pictures and figure out the answer from some pictures. So think of this E, this is, so they're slightly split anyway, right? They're not exactly at the same point. So let's draw the E and an M here, and then draw the E prime and an M prime here. Okay, is this going to work? Yeah. True. So the string should not really touch. So you can have a string like that and like that. Yeah, you're right. I mean, you have to do the strings properly. Just make sure that they don't cross each other right away. Okay. I thought I had a neat agreement neat idea when I woke up this morning, but it seems to have, maybe I was dreaming, Oh, excellent. Yes. No, it does work. M here and E here. By the way, this mutual statistics, because it's -1, it doesn't matter whether you do it clockwise or anti-clockwise. So we exchange them. So what happens is that this E prime goes to this E, this E goes to this E prime, this M prime goes to this M, and this M goes to this M prime, right? But you can see that's really the same picture as this, because the M is always inside the E curve, right? So this, you can adiabatically map it to this situation where these two M, this M is not moving and E is going in a closed curve around it. Sorry? Yeah, I know, yes. Yes, true. Okay, so this tells you that this exchange of these two particles gives you a phase change of -1. Okay, so exchange of two EM composite particles gives you a phase change of -1. So, that means this composite fermions particles are fermions, right, because if you exchange two of them you get a minus sign. So, it is all very strange, right. E by itself is a boson, M by itself is a boson, E going around an M is -1, but exchanging a EM with an EM is -1. Right? Yeah. Right. Okay, so now I can probably explain a little bit better why these are called electric and magnetic charges. So, the idea is that you can, if you want, you can interpret this thing as a kind of Aharonov-Bohm phase, right. So, you can say that associated with M, there is a flux coming out of the board, magnetic flux coming out of the board, and the E is associated with the charge. So, in this process, you have a magnetic flux coming out and there is a E which is going around it. And so, you can interpret this phase change of -1 as a kind of Aharonov-Bohm phase with a particular for a particular value of the charge times the magnetic flux. So, that is one way, that is one reason why it is nice to call these electric and magnetic charges, because then you can understand this fermionic statistics from the fact that E and M going around each other pick up a Aharonov-Bohm phase. Okay. Yeah, it does not matter. If you took an M around an E, you would still get a -1. So, I could have drawn the picture the other way. I could have taken the E inside and the M outside. Yeah, it does not really matter. You can either say E, a charge going around a magnetic flux, or a flux going around a magnetic charge. Either way, you pick up a Aharonov-Bohm phase. Okay, I think I am done. So, that is really all I had to say about the toric code. Okay.
Before I do that, I should tell you what that is. So, the first part of the talk will be a leisurely introduction, and that I think is the more important part of the talk. And after that, if we do not have time for the results, that is okay. So, let us start. I am saying this because this is supposed to be in the middle of a school. So, as I am sure people have emphasized to you earlier in the school, or you have learnt earlier, when you think in terms of band theory of solids, you are really thinking in terms of electrons as waves, and your crystal is some sort of waveguide, and you look for allowed modes, and then you invoke Fermi statistics to say each mode can be filled by two particles, one with upspin, one with downspin, and that is sort of the wave picture. And that tells us that if you have bands which are half filled, you would get a very good metal, you will get conduction because the bands tilt when you apply an electric field. On the other hand, if you have strong electron-electron interactions, it does not actually pay to think like this in this wave picture. It is much better to exploit the fact that in quantum mechanics you can think of the same system both as particles and as waves. So, you can start from the particle end, you can think of these simply as charged objects that like to stay as far away from each other as possible. And then you can realize very quickly that the electrons would just localize on lattice sites in some pattern that minimizes the Coulomb energy and freezes their motion, their translational motion. And when that happens, the only degree of freedom that remains is the spin, and that is where all your spin models come from, right. So, the charge degree of freedom is not completely frozen, of course. In quantum mechanics, you can always have virtual fluctuations. And so, here I am showing two electrons with up spin, and here I am showing two electrons, one up, one down, on neighboring lattice sites, neighboring ions, let us say. These might be the outermost electrons on these ions, and the Coulomb repulsion keeps them apart. So, in the low energy Hilbert space, you like to have one particle per site, one electron per site. If the spin arrangement is like this, there is not even a virtual process possible by which the electron can hop here and come back because of Pauli exclusion. But if the spins are anti-aligned, it is possible. And as we know, second order perturbation theory always lowers the energy. These virtual fluctuations always lower the energy. And this is a simple argument suggesting that such patterns of spins will have lower energy than those. And that's the origin of what we know as the exchange interaction between localized magnetic moments in solids, right. Now, this was too crude a picture, and the actual calculation of exchange couplings is actually quite complicated, involves a fair amount of quantum chemistry. You can have multiple orbitals that are active, you may have fluctuations between orbitals. So, there is a lot of physics there that is outside of the purview of very simple descriptions like that. This is correct if you have exactly one orbital per site and strong repulsion. But in general, in any particular experimental material, you do not really know what J is by a first principles calculation often. But there are some thumb rules which go under the name of Goodenough, Kanamori, Anderson rules, which tell you when J is positive, when it is large, when it is ferromagnetic, when it is very weak, things like that, which we do not go into here. We will be considering cases where J is large and positive to a first approximation. Okay? That is anti-ferromagnetism. There are of course complications to this story that come from spin orbit coupling, where the spin degree of freedom is coupled to the orbital motion of the electron. That is a relativistic effect, so it is weak except in heavy ions, but it can be important in many cases. And like I said, orbital degeneracy. So, let us start with the simplest case where we have J greater than 0, and we would like to ask what do these spins like to do. So, if you think of them classically, think of them just as unit vectors or vectors of some magnitude, then it is clear what minimizes an energy function like that. You just, if you are on a bipartite lattice, you could just pick one sublattice and get all the spins on that sublattice to point along some spontaneously chosen direction n in spin space, and on the other sublattice, and that is what this -1 to the r means, you would point them opposite. And this would be the global minimum of the energy, and in making this state you would have spontaneously chosen one vector, right. That would be a symmetry breaking, and it would lead to what is called nail order, right. This does not work if your lattice has triangles in its nearest neighbor connectivity defined in terms of the nearest neighbor exchange couplings. If you have this and you pick any axis n to try and do this with, if this spin points up along that axis, that one points down, this spin does not know what to do, right. Of course, nobody guarantees that the system will always pick collinear states, and that is actually the resolution to the problem in many cases, but at least it is clear that having triangles in the nearest neighbor connectivity with antiferromagnetic couplings will frustrate nail order, right. That is the origin of the geometric frustration in many systems. And the reason frustration is so important and interesting is that when you have this sort of a situation, the leading exchange coupling, which is J, becomes terribly ineffective at deciding what happens at low temperature. In some sense, it gets quenched in the same way that the kinetic energy of electrons gets quenched in a Landau level. It can't split degeneracies, right. And so, what really happens at low temperatures, what is the ultimate fate of the system, depends on subleading effects and on quantum fluctuations, and can lead to a variety of novel states. That is sort of the underlying interest in what we study, and I am sure you have heard a lot about this from John Chalker in the last 2 days, 3 days. So, this is just meant to be a quick review. The thing I would like to emphasize here is that although I started by talking about isotropic Heisenberg exchange with interactions of the form S dot S, single and anisotropy terms coming from spin orbit coupling can actually be quite large in many classes of materials, and I have just made some list from the literature here. You know, the famous pyrochlore spin ice materials, they all have some large effective spin coming from the combination of orbital and spin angular momentum, and in the effective value of J, which includes some dipolar effects, tends to be actually smaller than the single ion anisotropy. And in many other cases as well, it can be of the same order or smaller than the single ion anisotropy. And in such cases, you can actually start from a model where the single ion anisotropy dominates, especially if it is of the easy axis type like that, favoring one axis, and then systematically study leading quantum effects in this kind of an expansion. but that's not our focus today. I just wanted to mention that it can be done. What I want to focus on today is this basic fact that anisotropy in many cases amplifies the effect of frustration. So, let us go back to the single triangle. If you insist that the spins have to point along or anti-parallel to a given unit vector n, to be along some axis n, as would be the case if you had strong single line anisotropy that picks an axis like there, then a single triangle does not have a unique low energy configuration. Like I showed earlier, if this is up and that is down along that axis, this one does not know what to do, or so there is fluctuations, there is multiple ground states, there is degeneracies. But if you do not have single line anisotropy, the same triangle is perfectly happy and knows that it should just make a coplanar state which are 120 degrees, in which the spins are 120 degrees apart. And if you take a Heisenberg antiferromagnet on a triangular lattice, even spin half, where this classical picture is not a priori valid, it turns out that this is a perfectly good description of the ground state. So, whereas if you had large single anisotropy, you would not be able to say that. You would not know what happens at this level, right. So, the effects of frustration can be enhanced by anisotropy. That is sort of the first point I want to make. And so, with that as the motivation, I am going to start by revisiting something that John Tucker has discussed already, which is the Ising antiferromagnet on a triangular lattice. And the way I would like to think of it as arising is by starting with a Heisenberg model on the triangular lattice with a very large single ion anisotropy term. So, any spin bigger than 1 or equal to 1, not spin half, that is all. Any spin bigger than 1, you will do this and you will realize that if there is a large single ion anisotropy like this, then to leading order Sz can only be plus S or minus S. The other states are disfavored by this term, and you can map that to an Ising model saying sigma equal to plus 1 corresponds to Sz equal to plus S and vice versa. And this will reduce to leading order in J over D to just the Ising model with antiferromagnetic couplings. So, you have already seen what the minimum energy configurations of this Ising model are. You must have seen a picture of this kind. So, on every triangle, you would like to make sure that all 3 spins do not point up or all 3 spins do not point down. So, if they do that, then it is maximally frustrated, all the bonds are unhappy, right. You would like to make as many bonds of every triangle happy as possible, and the number you can make happy optimally is 2. 1 you have to keep unhappy, right. 1 bond will have to have a pair of aligned spins on it, because this is an odd circuit, and 2 of them can have anti-aligned spins across it and be happy, right. The bond that's got aligned spins across it is the frustrated bond. And so, the rule for constructing ground state configurations of the classical Ising model is that every triangle must have exactly 1 frustrated bond, right. That you can think of as a honeycomb lattice dimer model by simply saying you put points down at the centers of every triangle and you agree that anytime there is a frustrated bond, you will draw a dimer perpendicular to it, connecting the 2 points at the 2 centers. So, let me show a picture of that here. So, ignore the title, this is the original triangular lattice, and these points which make a honeycomb lattice are at the centers of the triangles, and the dimers would live on the links of this honeycomb lattice. We will come back to this. So, many years ago, there was a calculation done by Wannier who used Pfaffian methods to compute the thermodynamics of this Ising model, and he found that unlike the ferromagnetic case, there is absolutely no phase transition all the way down to 0 temperature, which was, I guess, at that time a surprising result. It took many more years, I think 14, before spin correlations could be calculated exactly, and that was done in this paper by Stephenson. And so I am quoting only the 0 temperature limit of his answer. He computed the answer at any temperature, but if you take the 0 temperature limit of his answer, this is what he got. So, you see, even at 0 temperature, the spins are not ordered because the correlation function decays to 0. Remember, if the correlation function doesn't decay to 0, that's a sign of long range order. Here the correlation function does decay to 0, but it decays to 0 even at 0 temperature in this power law way. And there are two powers here. There is a dominant power which is 1 over square root r, but it has got an oscillating prefactor, right. And then there is a subdominating power 1 over r to the 9 halves, which is smooth. Okay. So, this was the calculation he did, and if you want to describe in words what this result is, you would say the spins neither freeze nor do they fluctuate independently like they would in a paramagnet. So, they are neither a gas nor a solid, instead they form some sort of highly correlated liquid, and this would be the simplest classical example of a spin liquid. So, let us try and before I go to the subject of the talk, let us just try and understand this result using things you have learned in the lectures earlier. So, and also let us make some small comments about some obvious connections to Ising gauge theories that connect to Diptiman's talk and some minor review of Kosterlitz-Thouless theory. Let us just talk about these things. So, first let us decide how we want to think about this result if we do not want to do a detailed Pfaffian calculation and get the exact answer. Okay. So, for the first thing we are going to do is we are going to give up on the original Ising model and instead start parametrizing things in terms of dimers. Like I said, there is a honeycomb lattice and there is one dimer touching every point of the honeycomb lattice. And we want to talk, and the ground state or the low temperature answer that Stephenson derived should be thought of as the average over all ground states of this Ising model, right. So, you want to average over all possible states that minimize the energy and ask what the correlations are, and this is the answer you are supposed to get. So, we want to understand where that came from. So, first we decide to parameterize these all possible ground states in terms of dimers, right. There is one dimer touching every honeycomb site. Okay. Now, you go from dimers to heights in the way John Chocker showed you, and let me just recap, at least in maybe my notation is slightly different. So, let me just say what I am doing. So, I start with some arbitrary point on the triangular lattice and the height is 0 over there. Okay. Then I make up a rule. So, the honeycomb lattice has A and B sites, it is bipartite. Then I make up a rule saying around every A site I will go anti-clockwise. If I do not encounter a dimer on a link, I will drop the height down by 1/3. So, from 0 I will go to minus 1/3. Then again I go from this minus 1/3 here to a minus 2/3, right. But if I do encounter a dimer in this anti-clockwise traversal around A, I will raise the height by 2/3. Okay. So, that is why this is 0, that is minus 1/3, minus 2/3. The corresponding rule for going around B sublattice sites is the same thing, but going clockwise. Okay. With this, you can see that you will get a consistent and unique up to a constant that you define by starting somewhere at 0. You will get a consistent assignment of heights that are integer divided by 3 throughout the lattice for every dimer cover, right. So, every Ising model ground state will become a configuration of these microscopic heights, where the capital H is supposed to tell you that I am talking of these microscopic heights, and capital R are points on the triangular lattice. Okay. All right. So, what have I done? Well, not much apparently. I started with Ising spins on the triangular lattice and I went to integers divided by 3 on the triangular lattice, and this is exact, right. But now here comes the non-trivial step, which again I am sure he explained. The usefulness of this approach is that now you can say, let us take boxes of some size, some coarse graining size, and split up my original lattice into these boxes, and let me agree to define an average height or a coarse grained height little h of r corresponding to each such box, and this is to be understood as the average over all possible ways of covering the lattice inside the box with dimers. Okay. So, that is the coarse graining we are going to try and imagine we are doing. We do not actually do it in practice, we just imagine we are doing it. And then the question becomes, if I were going to do an average where I average over all ground states of the Ising model with equal weight, what weight function should I use in terms of these coarse grained height variables to do the same average. Okay? And clearly this is something one needs to answer if one wants to trade in the microscopic heights for this coarse grained height variable and work with these blocks. Okay? And before I address that, in the end we are going to write down some effective free energy functional for these heights, these coarse grained heights, that describes what weight I will assign to each coarse grained height configuration. And before I tell you what that function is, I want to constrain that function by thinking in terms of symmetries. So I want to ask, if I use symmetries, what do I know about what that functional should be, that action and functional in terms of which I want to write everything, right? So one very basic thing, which is not even a symmetry, which is a statement of locality, is the idea that what happens inside my box shouldn't care about the boundary of the box that I am fixing. So I think this I should draw. So this is my box, and to be able to cleanly distinguish between what's happening inside and outside, I agree to tile my box with an alternating pattern of dimers like this, so that there's a perfect dimer cover of the boundary that disconnects the interior from the exterior, right? Now, and here is some point which is the origin of the heights, which is the origin of space and the origin of the heights. The height is 0 here, right? Now, inside there will be all sorts of dimer covers possible, and the average over them is little h, and the weight I want to assign to that configuration of little h depends on how many different things there are that I can do inside. That's the weight function I'm trying to get, right? That answer is not going to change if I just cyclically flip these guys, right? Because what happens inside will keep happening inside, right? But a cyclic flip of these guys, where this goes here like this, like that, will actually change all the heights inside by +1 relative to the old heights. Why? Because originally I would have gone from this side to a site inside via the dimer. Now I'll go via an empty link, and so instead of going up by 2/3, I'll go down by 1/3, and that's a difference of 1. So HR going to HR plus 1 is not even a symmetry, it's more a redundancy, right? It says that exactly the same configuration is being described whether you say I'm using HR or I globally shift H of R by 1, okay? The origin is outside. No, the whole sample is here, and I'm starting with the corner of the sample outside. I'm allowed to do that, right? It's got to make the cleanest possible way of coarse graining, and this is 1. Right? So this is not a symmetry, it's a redundancy, right? This is a redundancy in the same sense in which you can describe position on a circle by an angle theta, but theta and theta plus 2 pi are the same thing, right? So in fact, field theorists like to call this a compactification radius by analogy to that, okay? So that's not a symmetry, that's a redundancy, we know what it is. Then you can play the same game and make arguments based on translation symmetry and rotations by 2 pi by 6 about a triangular side. And you will learn that by doing suitable combinations of these symmetries, you can either send H of R to H of R plus 1/3 or H of R to minus H of R. So these are the two symmetries, and that's the redundancy, okay? So whatever height, whatever functional we write down to describe the weight of configurations relative to each other should obey these symmetries, okay? So symmetries don't alone dictate what you should write down. There is a physical argument, and I'm sure you heard the argument in the school earlier. And the idea there is that if you have fewer flippable plaquettes, so this is a flippable plaquette. Because there are two tilings of this obtained by flipping relative to each other. So if you have lots of these, there's lots of local rearrangement possible. That means there's lots of nearby dimer states. That means when you coarse grain over things, there'll be more weight for the height configuration, the coarse grained height configuration corresponding to such states with lots of flippable plaquettes, right? And you can check just by drawing out pictures, as you probably did earlier, that when you don't have flippable plaquettes, you actually get an average tilt of the height. It's like there's a surface and it's just climbing up. and so that has very few nearby states. So the statement is that there's an entropic cost to tilts, and the best way to put that in, preserving all the symmetries we described, is just a gradient h square. Okay. So one term in the effective action has got to be a gradient h square with a coefficient, that's the leading term, and then the symmetries allow all sorts of cosines. The first one is this lambda 6 cos 6 pi h. Okay. So that is the effective action, and so now the partition sum will be, it's just a constant I know nothing about at this stage. This is a phenomenological description. So there's some number there, I'm writing it as pi divided by g for a reason that will become obvious soon. There's just some number. So now we are going to say that the partition sum is actually the path integral of this with this action, instead of just adding up all microscopic configurations with equal weight, right. So that's the idea. So with this we can now understand Stephenson's result if we could understand how to write down spin operators, how to write down the Ising spins in this language. Okay. And that you have to make a similar argument. What you can do is you can show that if you are working with microscopic heights, there's two ways of writing the same thing down, and the two ways are these. You either take 3I pi capital H. So spin at 0 is up, and you are asking what's the spin at r, this is r. And there's two ways you can do it microscopically. One of them will give you this expression, and that's microscopically exactly equal to this expression. I can show this to you later if you like, but trust me that these are exactly identical at the microscopic level. But once I coarse grain, they are not identical. So what am I supposed to do? Should I believe this or should I believe that? Well, the answer is you should believe both, and you should understand that when you do the coarse grain analysis, the spin operator has two pieces. One piece is inherited from this way of writing the answer, and the other piece is inherited from that way of writing the answer. And so the spin field is to be written as something with an oscillating prefactor, which is e to the minus I pi h. Of course, there is a Hermitian conjugate as well. And then another piece which is e to the minus 3 I pi h. Okay. So that's the spin field, and you want to calculate correlations of this operator now in this effective action. This is something we learn how to do in grad school. It's a Gaussian integral that you have to perform if these cosines can be rendered negligible. And one of the basic sort of ansatz you make is that this liquid phase corresponds to a regime in which G takes such a value that this is irrelevant in the renormalization group sense. So then you should do the average just with this. And so then you really have a simple calculation to do. You have to calculate the correlator of this in that Gaussian theory. And when you do that, you will immediately learn that there will be two powers. One power, whatever it is, will have an oscillating prefactor, and then there will be a smooth power law without oscillations, which will have a power which is 9 times this power. That much you know, right? Then you just say that G is whatever I get to get the right answer for one of the powers. So you know that Stephenson got 1 over root r, so it turns out that G has to be half. Okay? So that's how you understand Stephenson's result in this coarse grained way without doing this very complicated Pfaffian calculation. Okay? And the advantage of this is much more generally applicable. Even when models are not exactly soluble, you can think like this. Okay? So this is sort of a digression just to connect with the school lectures. Let's now move on. But before I do, let me connect with some other things that were said. So I mean, short of an exact solution, you never know a phenomenological parameter, right? So I don't know, yeah, I would say no. Is that true, John? Yeah. I mean, it's very easy to change G by just changing the Hamiltonian slightly. So, you know, add a second neighbor coupling to the Ising model, it's not soluble anymore, G changes a little. This analysis goes through, but it's not soluble anymore, not a solvable model. Okay, so some comments connecting it with other things you have heard. So first of all, what happens at non-zero temperature? At non-zero temperature, you are now suddenly allowed to make triangles that have all 3 spins up or all 3 spins down, fully frustrated triangles, right? These are not minimum energy, but okay, you will pay a Boltzmann cost, energy, you know, e to the minus 3j over t, but t is non-zero, you are allowed to do that, okay? What do they correspond to in this height picture? Well, they are a vortex in the following sense. If you check what happens with a fully frustrated Ising triangle, it corresponds to 3 dimers touching a point. Okay? When 3 dimers touch a point, you go up 2/3, 2/3, 2/3. That means in a cycle around that point, you change the height by 2. There is an ambiguity of 2 when you go around a point, right? So that's a double vortex in the language. If you call h going to h+1 a single vortex, this is a double vortex. Okay? And so you should think of 0 temperature as Kosterlitz-Thouless theory, or the theory of the XY model in which vortices have been suppressed by hand, and non-zero temperature as allowing vortices, which is the generic case. Okay? The second thing that happens is that the configuration space now is, you can still think in terms of dimers, but the constraint is not 1 dimer touches every point of the honeycomb lattice, it is an odd number of dimers touches each honeycomb point, right. And that, if you think about it, is exactly the configuration space of an odd Ising gauge theory, which is closely related to, well, the even case is closely related to the toric code Deeptiman just told us about, right. So that's the other aside I wanted to mention before moving on. Okay. So today, with that background, now let me tell you what I want to do. So I want to think about easy axis antiferromagnets on the Kagome or triangular lattices. The Kagome lattice is simply this lattice which is a triangular lattice of up pointing triangles. So every point here is replaced by a up pointing triangle. Okay. And both have a natural tripartite structure. This is A, B, C, A, B, C. This is the tripartite decomposition of the triangular lattice, similar here. There are A triangles, B triangles, C triangles. Okay. The only difference is that there is a 3-side basis which is not here, there is a single side here. A very natural way for systems to order on such lattices is 3 sublattice order, where the ordering pattern kind of knows about this underlying tripartite structure. So here I am drawing a picture. So the color coding of the dots tells you what the value of the spin is of this easy axis antiferromagnet. Remember, it can only be pluses or minuses because of the strong anisotropy. Okay. So in one state, which I am calling theta equal to 0, you will see why. The red dots all are minuses, they point down, and every dot, red dot, which is pointing down, is surrounded by a hexagon of up and down pointing dots alternately. Okay. This is one kind of state you can make. This is 1 out of 6 equivalent ones actually, related by symmetry, because there is 3 choices for which sublattice to put the down spin on, which is in this case the minority spin, but then you could also have the minority spin being up. So there is basically 3 choices to decide where the minority spin sits, and then 2 choices to decide whether the minority spin is up or down. So that is 6 equivalent states related by symmetry, related by lattice symmetries. So that is one kind of 3 sublattice ordered state. This one, if you notice, has a net moment. The A sublattice, if it is down, the other 2 are up. So that means there is a net moment which is 1/3 of the saturation magnetization. There is another 3 sublattice ordered state you can make which has no net moment, because you pick randomly one sublattice where the spins are wildly fluctuating. Wildly fluctuating means either pointing along a transverse direction, if it is a quantum problem you are talking about, or just with thermal fluctuations fluctuating up and down. Okay. So on average 0. And then there is 2 choices for what to do with the other 2 sublattices. One of them will point up, one of them will point down. Yeah. This is the vacancies on a particular sublattice. That is right. So that is the other one. That is what I am trying to tell you. So there is one set of 6 states which are ferrimagnetic and 3 sublattice ordered, and there is another set of 6 states which are anti-ferromagnetic and 3 sublattice ordered, where there is no net moment. What you are calling vacancies, I am calling wildly fluctuating spins. Okay. No net polarization on average. The reason I am labeling them by 0 or pi by 6 is because the order parameter I construct to derive a Landau theory would be this sum, where I add up the spins with this phase factor, which is the 3 sublattice wave vector. This is the same phase factor that appeared in Stephenson's solution, we will see. Okay. And so this is a complex number, it has an argument and a phase, it has a modulus and an argument, and this argument is this theta. So, either this theta can be 2 pi m by 6 where m goes from 0 to 5, or it can be 2 m plus 1 pi by 6. If it is 2 pi m by 6, it is ferrimagnetic and the other 6 are anti-ferromagnetic. Okay? So, there is two kinds of 3 sublattice orders possible on the triangular lattice. This is just kinematics if you wish, I am just describing the states. Same story on the Kagome, a little bit more detail, but again there is ferrimagnetic or anti-ferromagnetic. You just have to decide what to do with these 3 sublattices inside the triangle, and there is a natural pattern here I have shown. Okay. So, these are natural 3 sublattice ordered states of easy axis magnets on both lattices. What I am going to be telling you about is how they melt. So, you get, imagine you have some perturbation, some subdominant coupling, some quantum fluctuations, and I will describe exactly what I am talking about, which seeds this order. And this is not hard to believe, because if you look at the result of Stephenson, the dominant behavior is actually a power law correlation as exactly this 3 sublattice wave vector. So, already without doing anything you are power law ordered. So, it is quite natural to imagine that at least on the triangular lattice that all sorts of perturbations might stabilize this order. Okay. So, that is what we are imagining happens, and we are asking how does it melt. So, I will show you that on general symmetry grounds there is 3 ways in which this could melt. The third is always possible, and I do not even need to tell you this. First order transitions can never be ruled out, that is always a possibility. So, there are really 2 other ways. One is a 2-step melting process where you go from long range order to power law order to paramagnet, and the intermediate phase is kind of the non-zero temperature analog of Stephenson's 0 temperature result, right, described by roughly speaking by a XY model in which vortices have been suppressed, right, which is what this effective height model description does at 0 temperature. Right. So, this would be the non-zero temperature analog of that, which would be an intermediate phase in this melting scenario. Or I will show you there can be just a 3-state Potts transition at which the 3 sublattice order is lost, followed by a regular ferromagnet to paramagnet transition at which the net moment disappears. Okay. So, this is another possibility, and this is just on very general symmetry grounds. And what I will hopefully convince you about in the next 15 minutes is that if there is an intermediate KT phase, then there is a very interesting and unusual thermodynamic signature of this power law order at non-zero wave vector. And this thermodynamic signature is obtained just by applying a uniform magnetic field to the system along the easy axis and asking what is the susceptibility, field dependent susceptibility. And I hope to convince you that the field dependent susceptibility in this KT phase is a universal power law with the power that can be predicted, and we know how the power varies in the phase. Okay. The other thing I want to tell you about is that this KT phase can, depending on microscopic parameters, get pinched off at a multi-critical point, giving, previous, okay. Sure. But I think just in terms of microscopic energetics, the other way around is a possibility in Landau theory, of course, but in terms of the microscopic energetics, all the cases I know it is this way around. That is why I did not bother to list it. I mean, there is another possibility of course where the 2 get reversed, but I do not know of an example where that happens. I will come to that. It has to do with the fact that ferrimagnetism is natural. That is the point. So, I will try to convince you that this KT phase can actually pinch off as a function of some microscopic coupling constants in the original Hamiltonian at multi-critical points that seem to come in 2 varieties. In one kind of pinch off, the temperature extent of the KT phase shrinks. So, there is temperature and there is some other parameter, the KT phase shrinks to nothingness, and on the other side you get these 2 other transitions, one Potts and one icing. That is one way, and the other is that on the other side you just get a first order transition. The fact that you can get a first order transition on the other side is well known, and in fact people way back 25 years have studied what might be the field theory for that, and it's supposed to be this conformal field theory with central charge 1.25. Okay. It was not studied in the context of two-step melting, but in the context of StatMech models in the same universality class. So I'll explain that to you. This multi-critical point is new as far as I know, and there doesn't seem to be a clear understanding of what its central charge is. At least I don't know. I'll show you some results, numerical results, not on the central charge, but on scaling dimensions. Yeah. Yeah. So these are all finite temperature transitions. So the low energy theory is always some 2D StatMech, right? Even if the underlying problem is quantum mechanical, you're driving a finite temperature transition, right? If you wish, the zero Matsubara mode of your quantum problem is your effective classical field. And then I'll try and show you that we have some quantitative verification using stochastic series expansion numerics of this predicted singular susceptibility in the KT phase, and we have some preliminary evidence for this better understood multi-critical point on the triangular lattice, and similar more preliminary results on the Kagome. So this is sort of an overview. Now it doesn't really matter if I get to the end or not, so let's see how far I get. So let me skip this. This was meant to tell you that these sorts of Ising models have a very long history, going back to studies of noble gas atoms adsorbed on graphite, where these served as models of the lattice gas of monolayers, and in that context they were studied quite a bit. And 3 sublattice ordering has actually been measured experimentally in these monolayer films. The picture is that the graphite hexagons, their centers are the triangular lattice site, and the noble gas atoms being big, they have some excluded volume type thing, which is the nearest neighbor repulsion of the Ising model. They have also been used as models for so-called artificial Kagome ice, which are honeycomb networks of micron-sized wires, and it's these magnetic moments of these magnetic wires. The energetics of those have been described in terms of Kagome lattice Ising models of this type. I'll have a little bit more to say about that later. Just to say that this is not something I'm pulling out of thin air. This has been studied a lot for 30 years. And then of course there's a prototypical example, which is the transverse field Ising antiferromagnet, where you just take Monier's model and put a transverse field. This was used as a prototype of quantum order by disorder in a very well known paper here by Roderick, Shivaji and Premi Chandra, and then later by Isakov and Messner. And in this case actually the ordering is of the antiferro type. So one sublattice fluctuates wildly and the others make an antiferromagnet. And the way you rationalize this is you think in this Daimer language, and in Daimer language the transverse field likes to do this flip of flippable hexagons. So you want patterns in Daimer language that maximize the number of flippable hexagons, and you can see very easily that this pattern does that. This example is perhaps not so easy to realize experimentally, although it's theoretically a great prototype, because if you really have an Ising model like this, it's likely to have large dipolar components to their energetics and screws up this nearest neighbor description. A more promising example might be something we looked at some years ago, which is to imagine that you have a triangular lattice antiferromagnet, Heisenberg antiferromagnet, with a easy axis single and anisotropy term that is large but not too large. And the point about being not too large is that corrections to the next order in JOD should be important, but not so important that they destroy what we are talking about. So if you do the first correction, you get this hopping term in boson language, which is unfrustrated, and then the Ising interaction becomes a frustrated repulsion between bosons. And this is known to have 3 sublattice ordering of this ferrimagnetic type that's been studied numerically by several people including us. What was not clear earlier is whether the 3 sublattice ordering is ferrimagnetic or not, and there was an argument again thinking in terms of these flippable motifs. In this example, the flippable motif is a double hexagon, and so there's a more complicated state that's possible, but actually what turns out to be the case is that it's ferrimagnetic 3 sublattice ordering, which is what this peak is supposed to show. So that's sort of the background, that there is this kind of ordering. It's seen in many models. It could have some experimental implications. So that's where we stand now. So now let's talk about symmetry breaking and Landau theory, because now I want to start thinking about the transition out of this long range ordered state. Okay. So usually we start with the order parameter. In this case, it's a complex number, and we write down a phenomenological free energy functional, which is just a polynomial in this that respects all symmetries, right? And then if you neglect spatial variations, you don't have any gradient terms as well. You just have this polynomial, and changes in the character of its minima are the transition. That's how you do it. And fluctuations, of course, can change the story, but usually they lead to corrections to exponents. They don't change the nature of the transition, except in some special cases where they can lead to first order behavior. And symmetries are usually decisive. It's the transformation properties of this order parameter under lattice symmetries that dictates what terms you can write in your polynomial, right? So if you follow that path, that well laid path here, you would write down a theory that looks like this in terms of that complex order parameter. And because the first anisotropy that breaks the U1 symmetry of this part is psi 6 plus psi star 6, it has the same symmetry as 6-state clock models with Z6 symmetry that was studied extensively in the 80s by Cardy and other people. Okay, so here in this lattice version, which is much simpler, the phase of psi can only take 5 values. Instead of there being an anisotropy, it's actually just restricted to 6 values. So 0 to 6. 0 to 5, and then you write down an energy term, which is the most general possible ones respecting these symmetries, and that's what was analyzed by Cardy with using a sort of a web of dualities. And so the simplest lattice model I could write down, which is the same as that Landau theory, is to just say there's a cosine theta I minus theta j with some ferromagnetic xy coupling, and then this anisotropy, 6-fold anisotropy. And it's this analysis of Cardy that shows for these 6-state clock models that you can have either 2-step melting or first order behavior, or a split transition where there's a 3-state pots and an icing transition. Okay. And as Shubhro point, yeah. Yes. Right. So I should say thank you. So roughly speaking, yes, it's really 2 ways of thinking about it. In the height language, I was starting at 0 temperature. I explicitly didn't have vortices. Here, I have vortices in this theta, but if I'm in a KT phase, they are suppressed, and so the physics is very similar. Okay. So it's this analysis of Cardy, as I was saying, that suggests these 3 possibilities. This one is actually 2 different possibilities, as Shubhro pointed out, and in the context of the 6-state clock model, you can make both happen, no problem. You just decide whether you want to crank that up or crank that up relative to K1. If you keep K1 equal to 1, crank up K3, you will first get a, coming up in temperature, you will first get a Potts transition, then an icing. If you crank up K2 instead of K3, you will first get an icing transition and then Potts. But if you think of the energetics of the microscopic anti-ferromagnet, that's 3 sublattice ordering, I can't think of an interaction that will effectively crank up K2 and not K3, whereas it's very easy to crank up K3. That's the point. Yeah. Was for this discrete clock models, 6-state. Yeah, so think of the clock angle as the phase of psi, except that I'm not pinning the phase of psi to 6 values. It's a continuous variable with 6-fold anisotropy. That's just whether the anisotropy is in the bare model is finite or infinite. The universality class should not change, right? It's the same symmetries. This is just numerically convenient, and it's convenient in terms of dualities to do this sort of duality, right? Because the duality becomes sort of a discrete Fourier transform when you think of models like this. Yeah.
This K1 and K2, these are some objects which you have no information about how they are related.
Yeah. So here I was just telling you what is the model Cardy solved. I'll come to our model. So right now when I'm talking about the microscopic models, Landau theory, I'm just taking the analog of K1. We'll come to that. And so let's ask what is the nature of the 3 sublattice ordering transition seen in all the examples I told you about. So if you think about the transverse field Ising model, there is this paper that explicitly demonstrates its 2-step melting. In lattice gas models, which are just classical Ising models on the triangular lattice with further neighbor ferromagnetic couplings, it's again 2-step melting. And so this immediately tells you that the nature of the transition is not tied to the nature of the ordered state, because this is ferrimagnetic, that's anti-ferromagnetic. Both of them are 2-step melting. Okay. Even more interestingly, more recent work suggests that if you take the Kagome problem and include long range dipolar couplings, you still get a ferrimagnetic low temperature state, but the transition is now a sequence of 2 with a 3-state pots followed by a ferromagnetic Ising transition. But if you cut off your dipolar couplings to second neighbor or third neighbor, you just get 2-step melting. So the nature of transition even depends on the range of the interaction. Okay. Not surprisingly, I mean it's some detail fixed by detailed energetics of domain walls, if you wish. So there was some argument in the literature where there was a paper that argued that the transition in the spin 1 Heisenberg antiferromagnet with strong EJ axis anisotropy should be this 3-state parts transition, and that's not something you can get right at a quantitative level by just arguments. So we've done the numerics and we find again a very clear 2-step melting region. This is not yet published. So now, given that there are many cases with 2-step melting possible, let me go to the first result I wanted to tell you about. This fact that there's lots of 2-step meltings possible in many examples is the motivation for asking, do I really need to do a scattering experiment to detect this power law version of Bragg peaks and detect this intermediate power law phase? If I have a power law ordered phase and the ordering is at a non-zero wave vector, it's kind of subtle to detect. You either got to do some real space imaging like people do in these vortex lattice systems and then do a lot of signal processing to then say it's power law ordered, or you got to do a scattering experiment, neutron scattering, something like that, and detect power law versions of Bragg peaks, which is subtle business, right? So the question is there some other way, at least in this specific example, where I could just make a thermodynamic measurement, just some easy measurement in the lab and say, yes, this is a clear signature of 2-step melting. And that's the first result that I wanted to tell you about. This is the claim. The uniform susceptibility in a field along the EZ axis, right? In the power law ordered Kostelis-Thouless phase will be singular, the field dependent susceptibility, and this exponent will be related to the power law exponent of the order parameter in this way. This is the claim, and I'll justify it in a minute. Okay. So this is a fairly strong power law. It varies from 1 over b to the 2/3 to then something very weak as you go up in temperature from the lower end of the KT phase up. So, and this is particularly interesting if the low temperature state is not ferrimagnetic, but anti-ferromagnetic, because then in the low temperature state, the ferromagnetic susceptibility is totally nondescript. It's just some order 1 number. And there's no singular field dependence, there's nothing. It's, as far as the ferromagnetic susceptibility is concerned, it's disordered. But then you heat it and the ferromagnetic susceptibility goes singular in the power law ordered phase. That's the prediction. Okay. And so let me explain where this comes from. And where this comes from is the following. In the phase with long range 3 sublattice order, the low temperature phase, this angle theta strongly feels the influence of this anisotropy. It's relevant and the theory is no longer Gaussian. And so theta locks into either 2 pi m by 6, one of these 6 states, or 2 m plus 1 pi by 6, depending on whether the ordering is ferrimagnetic or anti-ferromagnetic, right? But when you heat it up, this becomes irrelevant. And roughly speaking, the phase of the order parameter is no longer pinned. It fluctuates uniformly on the circle, roughly speaking. And what this means is that some fraction of the times the power law ordered state is ferrimagnetic and other times it's anti-ferromagnetic. So it samples all possible values of theta uniformly, right? That's the meaning of this term being irrelevant. And so then it's not so hard to believe that the fraction of the times it's ferrimagnetically ordered, it develops a singular susceptibility to a uniform field. That's the physical picture I have for this result. But of course, the calculation is more serious. It's not just this picture. One can do a straightforward RG analysis and check that this is true. But that's the underlying reason. The pinning becomes irrelevant, and you fluctuate between antiferromagnetically ordered and ferrimagnetically ordered states freely. And that's the meaning, that's the pictorial representation in my mind of this power law phase. Okay. So, you can do a more formal RG description, which I don't think I should go into here. You write down the standard sort of fixed point action for the KT phase, and this in this regime of G 1/9 to 1/4, both vortices and 6-fold anisotropy are irrelevant, and so this is the Gaussian action you can use. And in this regime, there are power law correlators with the exponent being just this G. Okay. So now you realize that symmetries actually allow a coupling between the uniform magnetization mode and the cube of the order parameter. Or if you want, you can think of it as lambda 3 m cos 3 theta. This term is allowed by symmetries. It's irrelevant along this fixed line, but it's dangerously irrelevant, in the sense that although it doesn't affect the physics of what theta is doing, the back reaction of this term on m makes the susceptibility, the ferromagnetic susceptibility singular. And so you can easily compute what it is, and in a finite size, the ferromagnetic susceptibility goes as, has a singular term which is 2 minus 9 eta, this power of L. And now if you want to know the answer in the thermodynamic limited non-zero field, you just replace L by the correlation length induced by a finite field, and that's what gives us this answer. Okay, so that's the RG argument. And one can do the calculation. Let me focus on the most dramatic example of the result, which is you're in the transverse field Ising model, where at low temperatures things are antiferromagnetically ordered, there is no ferromagnetic response. You heat it up, this is, so what I am showing here is the L dependent susceptibility for the order parameter and for the uniform mode, sorry, this is overlapped. And so the order parameter grows as L to the 2 minus eta, this grows as L to the 2 minus 9 eta, but it still grows as a power law, and this is the finite size version of this prediction. So that's the confirmation. So now I can take this more seriously, this coupling of m to theta, and say I shouldn't really work with a Landau theory just for psi, because sometimes there are ferrimagnetic ground states, sometimes not, and the intermediate temperature state corresponds to fluctuations between both. So I must include the uniform magnetization mode in my description. So you should write down a coupled Landau theory for theta and an Ising field tau, which is the direction of the local magnetization. Okay. And so now you can analyze this model and learn this. You can see that as the strength of the ferromagnetic coupling that is induced between the local magnetization goes up, you can go from two-step melting to this sequence of transitions with Potts and Ising. So it's a busy slide, but this physics is just this. So if you have second or third neighbor ferromagnetic couplings, that will drive effective ferromagnetic interaction for these tau variables, which are the uniform magnetization mode's direction, right. Then you can drive the transition from power law order intermediate state to this sequence of two transitions. That's a possibility. It's also possible that you drive the transition from this to just first order. That you can't rule out. You have to see what happens in individual cases. The interesting thing is, without thinking in terms of this additional magnetization mode, yeah, you would never get a phase diagram like this. If you just work with the Landau theory for psi, the only multicritical points you have are these, where on the other side you just have a first order line. And that's clear from Cardy's analysis. So this is a different kind of multicriticality potentially. So we have investigated this, and here are the exponents for this new multicritical point numerically by just simulating this effective classical model and these numbers. So this is the basic exponent for psi, which is e to the I theta. And then you can measure exponents for e to the 2i theta and 3i theta. These are the three distinct exponents you can measure, and these numbers should be contrasted with the other kind of transition where on the other side there is a first order line. Now, there is an old prediction in the context of 6-state clock models that this kind of multi-critical point on the blackboard here corresponds to a particular self-dual conformal field theory with Z6 symmetry, supposed to have a central charge of 1.25, and there are some predictions for the exponents. And you can see these numbers, 3 theta being 3/8 and 2 theta being 1/3, are very different from the numerical measurements here, 3 theta and 2 theta. And so, these are clearly two different universality classes, perhaps not surprising, but I was confused at the beginning. But unlike this one where there is an explicit description, I do not think we really know what this multi-critical point is. The last two slides I would have shown, but I will not, is that we have preliminary evidence that this is what happens in the microscopic triangular lattice Ising antiferromagnet when you crank up further neighbor couplings. Do not worry about the axis, this is just a way of cranking up further neighbor couplings to induce more ferromagnetic tendencies in the model. So, you pinch this phase off and you get a first order transition, and we have preliminary evidence that indeed in the vicinity of this multi-critical point we see these Zamolodchikov-Fatih exponents. So, with that let me stop. Thank you.